Hey guys, doing another video here on our last week. It was brought to my attention there was a question that was a little bit difficult here on week 6 of the electrode course for morning class. I began looking at that question for everybody and it was something we all struggled with. So I thought, even though it's our finals week, it's a good teaching opportunity. I think we should take a look at it because it's going to benefit you guys. This is a really great example of a very simple circuit that seems a lot more complicated than it is, okay? And we're gonna work through it together, see if we can figure it out. So the question that I'm talking about was on the exhaust gas sensor. For week 6, it was the actual course part, I believe, and it's a very simple circuit. It was question number 4 and 5, I think, were the ones we really struggled with. And as you'll find out as we work through this, you'll see that they relate back to very basic circuits that we covered. Of course, that was a long time ago, but very simple stuff if you just kind of look past the different values we have going on and the fact that this is an advanced engine performance circuit. If we disregard some of that stuff, this is a very basic series circuit that we can work with, okay, pretty easily. So first of all, we're going to be using Ohm's law. All right, we talked about this, how to find information in the circuit. There we go. We're going to be using that again today. In fact, this is our main go-to. The other equation that we need was given to you in the question, which is just calculating total resistance. And actually, if you guys remember back to basic series circuits and calculating resistance values, that's also something that you probably already knew. Maybe didn't realize it because of what you were looking at. All right. The other one is calculating total resistance. And remember, in a series circuit, which basically has a start line and a finish line, we aren't dealing with any extra branches in this circuit. We just add up the resistances, and that gives us total. So if we have 2 ohms on one thing, 2 ohms on another, 4 ohms of total circuit resistance. Not too bad. Let's go ahead and draw this circuit on the board. So we have our control module, our ECM, with a 5-volt reference, and then we also have a built-in resistor, and that's a 1K ohm resistor. So if we have 1,000 ohms of resistance within that computer, that just helps it diagnose and read that circuit. Read the circuit essentially. All right, here's our output where we're actually testing and getting values at. So we're actually looking at what value the computer is going to see from this circuit, and that's how it knows what's going on, right? We've discussed this many times now. All right, so then our circuit continues on to our thermistor, our variable thermistor. In this case, it's PTC. Remember I talked to you about being a couple instances where we use PTC, which means when temperature goes up, resistance goes up. We do see that in exhaust gas sensors. The example I think I used in class a lot was protection devices on hybrid and electric vehicles. Okay, but this is an area that we do see this. Again, it's very simple, okay? All right, and then that, of course, goes to ground, which is the exhaust, right? It's in the exhaust, so the exhaust acts as the ground. Okay, so this looks a little bit more complicated, but basically, if I was to draw this again in basic circuit form, we have a positive, we have a circuit, and we have our negative with a resistor and another resistor. That's all that this is. Okay, we're working on a basic series circuit. Okay, so if you can look at it like that, sometimes that'll help you make it feel a little more, make you feel a little more comfortable diagnosing it, going back to those very, very basic series circuits. So the first question that we got that people struggled with was if this had 0 resistance, what would the computer be reading? What value would the computer see if we had 0 resistance right here? Now what does that mean if this sensor has 0 resistance? Essentially, it's a conductor. Now it's just a wire to ground. So we just eliminated our resistor right there. Now when we send voltage into a circuit, our voltage is going to get dedicated to the resistors, right? Or the resistances, the loads in the circuit. So if we now no longer have a load here, but we still have our load here, 1,000 ohms, what is gonna happen to all of our voltage? We know if we had two, that voltage would get dedicated to both. It gets split up, right? We remember that. But now if we don't have anything here, all of our voltage gets dedicated to the one resistance left, okay? So if we were to do a voltage drop here with our meter, we can't, of course, because it's in the computer. But you guys should know if we do a voltage drop here, how much voltage is it gonna use? It's gonna use all of it. It's the only load in the system right now if we have no resistance here, okay? It's gonna use all 5 volts, which means what reading are we gonna get right here on our meter? 0 volts, because we used it all up. So if this is reading 0 resistance, which it can, the computer is gonna see 0 volts, all right? So that was our first one. Let's go ahead and get rid of this stuff here. Okay, so now we're back to the one that we really struggled with, all right? And that's calculating how much volts the computer is gonna see at a certain exhaust temperature, all right? And the question tells us we need to decide what it is at 250 degrees Celsius. Now there was a chart on your thing that, on your lesson that told you a certain value. With that, you had to move the little scale and essentially simulate 250 degrees. And that gave you a value, and that value was 2,125 ohms of resistance at 250 degrees, okay? So we needed that first. Now, we need to calculate total resistance, so entire resistance of this circuit. Total resistance, it's a basic series circuit, so we take one resistor and we add it to the other resistor, all right? We know this one's 1,000, and we just found out that this one's 2125 ohms, okay? We simply add those two together, and what's that make? 3,125 ohms of resistance. That's total circuit resistance, easy, okay? So we know our first value. Now we can apply our Ohm's law and figure out what total circuit current is gonna be, because we need that to figure out just the voltage value, right? We need to know 2 items to figure something else out. So right now we need to figure out total current of the circuit. All right, so we're gonna take what we just did, okay? We know our volts, it's 5 volts, right? It's a 5-volt reference circuit, so it's 5 volts, easy. So I, or I guess we could call that total current, okay, is gonna equal 5 volts divided by 3,125, okay? I plugged volts in there, I plugged ohms in there for resistance, and here's our equation. Okay, I'm keeping this in big units, I'm not using millis just to make it easier on my part as a technician. That's what I would do too, okay? Just keep it in one form, then we don't have to do all the variables and exponents and stuff. So, if you enter that into your calculator, okay, you'll get 0.0016 amps. All right, so now we know total current flow in the circuit. So let's get rid of some of this stuff. So the main point was to figure out how much voltage this computer should see at that temperature, okay? We don't care how much is dedicated up here, all right? That's kind of a fixed, a known variable for the computer. We want to apply it just to this resistor here, okay? And now that we know this resistance, and now we know total current in the circuit, we can apply that again to our Ohm's law and figure out exactly how many volts is being dedicated to this circuit and ultimately is being seen by the ECM. All right, so this one's pretty simple also. You guys can see V over IR. So we know R. Okay, we know I, current. And they're next to each other. So we times them together. That's going to equal our volts. So our volts equal 3.4. Okay, now electude is set up to where if you get close, it accounts for maybe you not setting the temperature just right or doing little things. So if you were close to 3.4 volts, it was gonna give you the answer, okay? 3.4, you could be, I think up to 3.5 or 3.3, and it would be okay, all right? So that is how many volts we would see right there. That is what the ECM is reading. It said it sees 3.4 volts, and the ECM knows our exhaust is at 250 degrees, all right? And then because of the way this system works with this PTC thermistor, this will increase as temperature increases, all right? So there's your answer. Pretty basic. We used total circuit resistance, adding this to this, and then we just used Ohm's law twice to figure out what we needed. First, total current, so we solved for I first, then we solved for V, okay? Once we knew that. That's all there is to it, okay? It's a very basic circuit. It seems more complicated. Sometimes you talk yourself out of making simple measurements or simple calculations, but that's really all this is. All these items that we deal with on vehicles, day to day, they all go back to those circuits we talked about, series and parallel. All right, not too bad. I hope this helps you guys. Again, that is a tough question, especially when you're starting out, but if you can just associate that with a simpler circuit, something we've done several times in this class, okay, you guys can all do this stuff. All right, so there you go. That's the video for today. Good luck on finals this week, and expect another video from me here closer to the end of the week. And good luck, and I'll talk to you guys soon. Okay.